Hello, everyone. Welcome. Good to see you all. Happy Monday. I hope you had a great weekend and are ready for some crazy weather this week. It's supposed to rain like crazy this year. We're supposed to get many, many feet of snow and all that kind of stuff. So that's kind of exciting. Also exciting is that it looks like the governor has lifted the stay-at-home order for now, which means that we can get some more things opened up, like outdoor dining and things like that. So that's just a nice relief and we know that it's the beginning of the end. Hopefully, fingers crossed, right? Um, let's see. I had Lewis Daniel had asked me to make a quick announcement, so I'm going to call on him. Lewis, would you like to make your announcement?
Yeah, thanks, Professor Tro. Hi, guys. My name's Lewis. I'm the LTA for the Environmental Horticulture Department at SBCC. And we have approval to have garden worker volunteers. So if anybody's interested in coming on campus and doing some garden work in the Lifescape Garden on the east side of campus, we'd love to have you. You just want to reach out to our head of department, Mike Ganella, and his email is ganella@sbcc.edu. And I'll put that in the chat for you as well. Depending on your work ethic too, we do pay student workers. So if you are into working outside in the garden, it's definitely a nice experience. The garden's on the bluffs right over the wharf, so you get a good view while you're doing it too.
Sounds great. Wow. Yeah, we have an amazing campus. It's really a shame we're not on campus right now, right? Looking at that view.
Yeah, totally.
Okay. Thank you so much. If you have any questions, there you got an email address you can send to, and thanks, Lewis, for making that announcement. Let's see. In terms of course details, I think everything is going as planned so far. Make sure you're getting my emails. I sent one out at the end of every week for the following week, right? And that's your to-do list for the week, and so that you can use that to kind of help you stay organized and stay on top of things. For those of you that weren't in my class last semester, the most important thing is to make sure you keep up on a regular basis, right? Chemistry is not the kind of class you really want to fall behind on. It's not the kind of class that you can learn everything the night before an exam, right? Some kinds of classes, those that require more memorization, maybe you can get away with falling behind a little bit, but in this class, you really can't, right? So I really encourage you to stay right up to speed. The Mastering Chemistry assignments force you to do that. So keep up with those and don't fall behind. Once you fall behind, it takes an extraordinary effort to catch back up. And even though it seems like class just started, we still have our first exam here right on the horizon. All right. It's February 11th, chapters 12, 14, and 15. For those of you that were not in my class last semester, the format of the exam is that you're going to take it on Canvas. It's all multiple choice. It will be severely time constrained because the idea is that this is not an open book, open resource exam, right? It's an exam where you have to answer the questions based on what you know. You will be allowed a periodic table. You will be allowed a table of constants, and I'll send you both of those before the exam so you can print them out or have them open on your computer. And in addition to that, you are allowed a one-page cheat sheet, okay? And on that one page, you can fill it up with whatever information you want, all right? And organize it well because ultimately you'll have to draw on that information during the exam, and you want to be able to find it easily, right? Because again, you'll be very time constrained. And the reason I'm making them time constrained is just to avoid giving people enough time to go out and look for things on the internet. Okay, that is not allowed. That is academic dishonesty. If you are taking the exam and looking up things on the internet, you are cheating, and you should feel horrible. All right, I want you to learn chemistry. It doesn't do you any good to cheat. You're only cheating yourself. Eventually, if this is a class you have to take for some reason, you'll have to learn the material. And I want to provide you that opportunity, and I'm going to do my best that I can to help you. Because of the way the exams are, the exams are weighted less in this online version of my class than they would be in the normal version. So if we were in class, exams would count a lot more than they do in this online version. And the difference is made up by the practice exams, which are like pre-exams that get you ready for the exam. All right, and so you'll see that pop up on Mastering, and it's basically a way for you to get ready for the exam. You can take that pre-test. I'm calling them pre-test for the first exam, and as you go through, you can figure out what you know and what you don't know, and that also counts for part of your grade. Okay, so the exam really has two parts: the pre-test part, which has no restrictions, no time restrictions. You work through it on your own time. You don't have to worry about, it's open resource, obviously. But use that to prepare for the actual exam, okay? And then your exam grade, of course, will be the pre-exam is part of it. The pre-test is part of your overall grade, and the exam is too. And if you want to know the relative weightings, just go to the Canvas homepage, open up the syllabus, and you can see the relative weightings of the different parts of this course, including the exams and the pre-tests. Does that make sense to everybody? Are there any questions?
So the pre-test is like graded. Is it graded kind of like the homeworks, where if you get it wrong once, you get so and so off, and then
Correct. That is correct.
Okay.
However, one thing about Mastering that can seem a little quirky at times is on a regular question, like where you have a numerical answer, since there's an infinite number of answers, it gives you 6 attempts, and I think you lose about 3 or 4% for every wrong attempt. However, on multiple choice questions, since there's only a limited number of answers, you lose a lot more credit for every wrong attempt, okay? The pre-test is all multiple choice. So I think what you lose is about, for each question, you lose 33% of the credit for each wrong answer. So you're gonna wanna be careful with the pre-test and not just guess, right? Because you'll lose a lot of credit for that, and that is gonna count for part of your grade. Does that answer your question?
Yeah.
And when does a pretest open?
Opens a week before the exam.
Okay.
Okay. Everything pretty much opens a week before it's due. That's kind of the way I have it set up. Great questions. Do you have any other questions or complaints or curses or confusions? All right.
I have a question on the chapter set, and I don't know if it's just because we haven't gone through it yet. There was a question about, there was a graph, let's see, and you had to put delta H. I can email you that question. That's probably better, but
Okay.
I was just confused, and I don't know if we're gonna go through it later.
Yeah. I'm not sure exactly which question is, Sophia, but for individual questions like that on individual problems, it's probably best if I answer those after class. So can you stick around for a little bit after class, and then we'll address that?
Yes.
Okay.
Thank you.
Perfect. Okay. Any other questions before we get going? All right. Well, thank you guys again for having your cameras on, and thank you for being here. I really appreciate everyone, all of you that come to the live lecture and have your cameras on and allow me to interact with you. It really makes it almost like a real class. Let's see. I have one more question here, Seth.
Hey, sorry. Yeah, my question was, it might have been oriented around the same, about the solubility curves.
Yes.
There was a question regarding it, and it was asking for like exact numbers.
Right.
When the graph only kind of gives you it by tens.
Yeah. You have to extrapolate, right? You have to learn you just have to read the graph. So for example, if you're asked for the solubility, let's say, of KCl at 45 degrees, right? You'd have to come up here and say, okay, 45 degrees is here. See, that's about maybe 40, maybe 41, right? So there's a little bit of margin of error built in, but you have to just read it off the graph.
Okay, so just trying to do your best to.
Yeah, and learn how to extrapolate a little bit, right? So if you have a number that's between two numbers, as long as you're close, right? You should, so like, for example, the solubility, let's say, of lead nitrate at 28, right? You'd go here to 28, you'd come up here, see 28 is around there. Okay, so it's probably 65. right? That's the way you do something like that. Yeah.
Awesome. Yeah, I was just
Yeah.
unsure because I didn't know how far we're going to be going
Yeah,
with it.
yeah, and as long as you're close, you should get credit for that. So that's built into the problem, a little bit of extra margin of error on the answer.
Sweet. Thanks.
Okay. Okay, let's see. Why won't this let me go up? Okay. Very good. So we are looking at solutions, right? And last time we learned a little bit about the energetics of solutions. We learned about solubility. We learned how temperature and pressure affect solubility, right? And we learned that it was different for solids and for solids dissolved in water compared to gases dissolved in water, right? So keep all that in mind. Today, we're going to focus on, first of all, specifying the concentration of a solution. And because of different kinds of applications, there's very many different kinds of units in which solution concentration can be expressed, okay? So we'll go through some of those today. And we will also start talking about some colligative properties and specifically the vapor pressure of solutions. Okay, so that's kind of what's on tap for today. So these are the different solution concentration terms. Did I go over this really quickly a little bit at the end of class last time? I did, right? Just really quickly. So, but today I want to dive into it a little bit more. Okay, so molarity. Remember, moles per liter solution. Molality, moles per kilogram solvent, all right? Mole fraction is moles of solute over moles of solute plus moles of solvent. In other words, the total number of moles. Mole percent is just mole fraction times 100. Parts by mass, another very common unit of concentration, is going to be whatever the mass of the solute is divided by the mass of the solution times some multiplication factor. And that multiplication factor depends on the three different types of parts by mass units that we have. So percent by mass is 100, parts per million is 10 to the 6, and parts per billion is 10 to the 9. Let me just give you a quick tip on these units. Whenever you see these kinds of units and you have to use them in calculations, let's say you have a solution that's say 10.2% sucrose, let's say, in water, okay? When you see that, when you see that, just write it down based on this formula, right? So when you see that, write 10.2 grams of sucrose per 100 grams solution, right? And then you can see that this is a conversion factor between grams of sucrose and grams of solution. People get caught up on this unit for some reason when it's written like this. But if you immediately translate and write it like this, most of the time when you use it in calculations, you're going to use it in this form, okay? Now, what if you have 10.2 parts per million sucrose? What's the difference? Well, it's very, very simple. Instead of the multiplier being 100, what is it for parts per million?
10 to the 6.
10 to the 6, right? So when you see this, again, you see this and you go, man, what do I do with that? You go 10.2 grams sucrose, but now instead of 100 gram solution, you have 10 to the 6 grams of solution, okay? And now notice this is a conversion factor between the solute and the solvent in terms of mass, right? So this is a very usable form of this unit. This is a very unusable form of that unit. All right. And if it was parts per billion, the only difference would be what? What would be in the denominator? Instead of 10 to the 6, it'd be?
10 to the 9.
10 to the 9th.
Exactly right. It'd just be 10 to the 9th. Okay. And then lastly, parts by volume percent is volume solute over volume solution times the multiplication factor. All right. So instead of grams, you'd have milliliters or liters or whatever you want to use, as long as you use the same unit in the numerator and denominator, it doesn't matter, right? Okay, very good. So let's work through an example where we look at these different kinds of units and how we might calculate concentrations in these different kinds of units. Okay, so here's this example, and we'll start it at the beginning here. Remember, especially for those of you that are new this semester, a lot of times, you start a problem, you read it, and you don't even know, well, gosh, I don't even know where to begin, right? If you get to that point where you go, okay, I don't even know where to begin, just always begin by sorting, right? What important pieces of information is the problem giving you? What is the problem asking you to find, right? So write down everything that's given. So in this case, we're given 20.2 milliliters of CH3OH, right? And it says it's dissolved into 100.0 milliliters of water, right, at 25 degrees Celsius. It tells us that the final volume, so the total volume, is equal to 118 milliliters. Okay, that's kind of weird. Why is it that when you mix two different things and you have 100 milliliters of this and 20 milliliters of that, and you don't get 120.2 milliliters? That's often the case when you form solutions, okay? The volumes are not additive. Obviously, if you mix 100 milliliters of water with 100 milliliters of water, you're gonna have 200 milliliters, all right? But when you mix two different substances, a lot of times their volumes are not additive. Why is that? The intermolecular forces are different, right? Between the methanol and the water. And so because of that, one way you can think of it is sort of like, imagine a beaker of marbles. And now let's say it fills the beaker to the very top. Now add sand to those marbles. You can get a lot of sand in there and not change the volume, right? Because the sand fills in the empty spaces between the marbles. It's a little bit like that. That would be an analogy, okay? So the volume of solutions when you mix a solute and a solvent aren't always additive. And you can kind of see this. Sometimes I make simple syrup at home, which is just sugar and water, right? And if you combine, half a cup of sugar and a half a cup of water, you don't get a cup of simple syrup, right? You actually get less, all right? For the very, very same kinds of reasons, all right? Okay, what else do we have here? The density of the water is given as being equal to 1.00 gram per milliliter, right? And the density of the methanol is given as 0.782 grams per milliliter, right? So now you have everything written down that's given in the problem, right? And what is it asking you to find? It's asking you to find concentration in all these different units, okay? So all these concentration units basically are a ratio of two things, right? Amount solute, mass solute, amount solute, total amount, right? So the idea is when you're going to calculate these concentrations, think about calculating the numerator, calculating the denominator, and then dividing one by the other, okay? That's kind of the way you want to think about it, all right? So we'll start with a molarity, okay? And we know that molarity is moles solute over liter of solution. So what are we going to do? We're going to go after these two things, right? We're going to get mole solute, we're going to get liter of solution, we're going to divide one by the other, all right? So what's the solute here? Is it methanol or water?
Methanol.
Methanol.
Right, because it's the minority component. So we're going to go, okay, we got to get moles of that. So we're going to start out with what's given, right? Which is milliliters, and we got to get that to moles, right? And what do we have? We have the density here, right? So that's good. We can go to grams, 0.782 grams per milliliter, right? And our milliliters cancel. But again, we need moles, so we're going to go to moles. That means we have to use the molar mass. The molar mass is 32.04, so 32.04 grams. Grams cancel. Now we have moles of methanol. We get 0.493 moles of methanol. So far, so good? All right. And then we need now liters of solution, right? Well, what are we going to use? We're going to use the total volume, right? The total volume is the milliliters of solution. So we're going to convert that to liters. And by the way, I think it's probably by now you can probably do that in your head. You don't need to take a separate step, but 118 milliliters times, and again, just for those of you that are new this semester, a milliliter is 10 to the minus 3 liters, right? So the way you do these conversions, you just write 10 to the minus 3 liters milliliter, right? This and this are the same thing. Milli means 10 to the minus 3, right? So you're literally writing 10 to the minus 3 liters over 10 to the minus 3 liters, except you're using the milli there as the abbreviation for that, right? So then, and you put that on the bottom so it cancels, right? And so you get 0.118 liters, all right? Now, of course, the other thing is by now you might be comfortable enough that you just go, oh, okay, 118 milliliters is 0.118 liters, right? You can do that in your head, right? Many of you. But if you still get stuck, just write it out every time. If you're in doubt, write it out, okay? All right, so now I have the moles of solute, liters of solution, so I can find the molarity, right? Molarity is equal to 0.493 moles divided by 0.118 liters, and that's equal to 4.18 molar. Okay? Does that make sense? Any questions? All right, good. Let's move on to B, molality. So again, we're going to write down what molality is. It is moles solute, right, per kilogram solvent. And again, we're going to go after each of these quantities. Let's find mole solute, kilogram solvent. Luckily, we already have mole solute from before, right? So all we need is kilogram solvent and kilograms of water. Well, let's see. Let's go back up here and see what we were given. We're given 100 milliliters of water, and we're given the density, right? So we can write 100 milliliters times 1.00 gram per milliliter. But of course, we need kilograms, right? So we're going to do one more step. Kilogram. And again, same thing here, right? 1 kilogram, 1 kilogram. Kilo and 10 to the third mean the same thing, right? So we're going to write one over the other, and we're going to write it in such a way that the grams cancel, right? And we get 0.100 kilograms of solvent. So the molality comes out to be equal to 0.493 moles, right? Which we know from before, divided by 0.100 kilogram of solvent, right? And that's equal to 4.93 molal. Yeah. Is that making sense? Okay, good. Now, percent by mass. And again, we're going to write out, what does that mean? Grams solute, grams solution times 100%, right? That's a definition of parts of percent by mass, okay? So again, we go after this and we go after this, right? Grams of solute, we don't have. We were given volume, but we have the density, so we can get to grams, right? So we have 20.2 milliliters times 0.782 grams per milliliter, right? That's the density, which was given right here. Okay. And that's going to give us grams. And that turns out to be equal to 15.8 grams of methanol, right? And then the mass of the solvent, we already know is 0.1 kilogram. So that's 100 grams, right? So mass, we can also figure it out just by doing the calculation one more time and stopping at grams, right? 1.00 gram per milliliter is equal to 100.0 grams of water, right? So far, so good. And then we can just figure out the mass percent. So grams of solute is how much?
15.8.
Correct. 15.8 grams. Now for the denominator, we need grams of solution, right? So that's mass solute plus mass solvent, right? So we just go 15.8 grams mass solute plus mass solvent, 100.0 grams, right? And that's this ratio, right? This is the grams of solution. We multiply that by 100%, right? And we get our percent by mass. Now, if this was instead of percent by mass, if it asked for parts per million, right? What would be different? What would be different down here?
Instead of multiplying by 100, you would multiply by 10 to the 6th.
Exactly right. Everybody get that? Instead of multiplying by 100, if it's parts per million, you'd multiply by 10 to the 6, right? Because that's the difference. If it was parts per billion, you'd multiply by 10 to the 9. Okay? All righty. Good. Now, what do we have left? We have mole fraction and mole percent. Okay, so part D, mole fraction. The symbol for mole fraction is chi. All right. So what we're going to be doing here is chi mole fraction of the solute, which is methanol. Okay. And that's going to be equal to what? Moles of the solute, right? So moles of methanol divided by total number of moles. All right. The answer for C was 13.6% by mass. Oh yeah, someone got it already. Thank you. Moles of methanol divided by moles of methanol plus moles of water. Okay. Remember, we already calculated moles of methanol in part A, 0.493. So this top part is 0.493 moles, right? This is also 0.493 moles, right? So we just need to figure out moles of water, right? So moles of water is equal to, we know we have 100 milliliters times the density, right? That gets us to grams, right? And then to get to moles, we're just going to use the molar mass, right? So 1 mole over 18.02 grams. And that cancels, and I get 5.55 moles of water. Okay. So then the mole fraction of methanol is going to be equal to what? The moles of methanol, which we know is 0.493, divided by the moles of methanol again, 493 plus the moles of water. Like that. All right. And that's equal to 0.0815. All right. And notice that this quantity is moles. Oops. I forgot to put moles here and moles here. Is moles over moles. So this does not have any units. Right. Okay. Lastly, mole percent. Well, that's easy. That's just mole fraction times 100. Right. So mole percent is equal to, multiply by that at 0.0815 times 100% is equal to 8.15%. Does that make sense? Taylor.
Just a quick question. So the mole fraction is a ratio. And
Correct.
it's unitless, and then the
Correct.
mole percent is just the percentage version of that ratio.
Correct. Right.
Okay.
So these are always going to differ by just a factor of 100, right? You get from here to here by multiplying by 100. You get from here to here by dividing by 100. Yep. Okay, you guys ready to try one yourself? All right, here we go. Let's use the poll and go ahead and try this on your own.
There is no options.
Yeah, I was just about to say that.
Oh, crap. Okay. Hang on for a second. That was my bad. Let's see. Hold on. I got let me give you the options. Just hang on for one quick second. I'm so sorry. Um, uh,
Why don't we work in the problem where you find the options?
sorry. Here we go. We're ready for you. I'm ready for you. You see my screen? Perfect.
Yep.
Sorry about that.
I don't think that's the right question.
You're right. Ouchie, 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 ouchie. Hold on. My bad. Oh, I'm so sorry, you guys. Hang on. Oh, Monday. Um, almost there. Okay, how's that?
I can't see anything.
What?
Oh,
Oh, I see. Yeah. I see what happened now. Do. Hold on. I'm getting there.
Professor Cho, you didn't have your coffee this morning.
Man, it must have been a really good weekend or something. Okay, how's that? Are we there?
Beautiful.
yes.
Okay. I did have my coffee. I had coffee this morning. I had coffee this afternoon, and obviously it didn't help.
I have COVID and you're getting the symptoms.
Yeah. Is that forgettability? All right. It is the weather's fault.
Professor Cho, do you by chance have the molar mass of NH3 on hand?
Yes, the molar mass of NH3 is 17 grams per mole.
Thank you.
Oh, 17, just use 17. It's only 2 sig figs on this one, so just 17 is fine. So just a quick little hint here in case you're getting stuck. Remember, molarity is moles of solute. The solute in this case is ammonia, right? And you have the grams, so you can get the moles. And then the denominator is liters of solution. So be careful with that. It's not liters of water, it's liters of solution, all right? How are you gonna get the liters of solution? Well, you know the mass of the solution. The mass of the solution is the sum of these two, right? And then you know the density, so you can get from the mass to the volume that way, okay? The poll should still be up. Can everybody still see it? Okay. Megan, I don't know what happened. You can still work out the problem though, Megan. I'm going to keep it open for like about another half a minute or so. So try to finish in the next half a minute and then I'll work it out. Okay, I'm going to end it here in just a second. So if you have if you can click in your final answer. 5, 4, 3, 2, 1, end. Okay, so what we got the right answer was D, and a lot of you got D, but some of you didn't. So really quick, let's have a look at this. What you got to do is you got to figure out moles of solute, right? Because you know molarity is moles solute over liter solution. So moles of solute, how are you going to get that? 35 grams times what? The molar mass, right? 17, or use the molar mass. That cancels and you get moles of solute, 2.06 moles of ammonia, right? And then you need liters of volume of solution, right? So you need to use the total mass of the solution, which is equal to 125 grams. Some of you only use the 90 grams, right? You got to use both, right? Because molarity, very important, is always solution, not just solvent. All right. So 125 grams times 0.898 grams per milliliter. And that cancels, and that gives you 139 milliliters, right? Then, is there a question? Oh, I see. Okay, then you do, then you go molarity is equal to 2.06 moles divided by 0.139 liters, right? And that's equal to 14.8 molar, which rounds to 15 molar. All right. Does that make sense? Questions, anybody? Okay, good. Let's move on. So you'll get a lot of practice with these concentration units. Concentration units are always, can be tricky, right? Even though it seems fairly straightforward, they can be tricky. So be very careful with concentration units. And again, you'll get more practice, especially with the after class assignment today. All right. And of course on the problem set. But now I want to switch gears a little bit and move on to a set of properties which are called colligative properties. And colligative properties are properties of a solution that depend on the number of particles in solution and not on the type. Okay, depend on the number of particles in solution and not on the type. And so what happens with colligative properties is you have to account for the kind of substance that is the solute. All right. So in other words, if the solute is a molecular substance, like this solution that contained ammonia, when ammonia dissolves, each mole of ammonia produces 1 mole of dissolved particles, right? Because this is a molecular compound. However, if you have a solution containing something like sodium chloride, what happens when sodium chloride gets into water? It dissociates, right? And so 1 mole of sodium chloride produces 2 moles of dissolved particles, all right? And so, for example, if I was looking at some colligative property and I was looking at the difference between a 1 molar solution of glucose and a 1 molar solution of sodium chloride, the effect would be greater in the sodium chloride solution, right? Why? Because sodium chloride dissociates, and for every mole that I dissolve, I get 2 moles of particles. Whereas molecular compounds like ammonia or glucose, right, when they dissolve, 1 mole of dissolved particles produces 1 mole of dissolved particles, okay? So we want to keep this in mind when we're thinking about colligative properties. A lot of colligative properties we can understand by thinking about concentrated solutions as being thirsty. All right. I want you to think about a concentrated solution as being thirsty. What is that? What is it? When you're thirsty, what do you want? You want water, right? So you want more solvent, right? You want more of that water when you're thirsty. So a concentrated solution is thirsty. And I'll give you a good example of this. Anybody recognize this picture?
Life of Pi.
Yeah, this is the life of Pi. So this guy was stuck in this lifeboat with this Bengal tiger out in the ocean, right? And he had to survive for many days. I can't remember how many days. It was like hundreds of days. But anyway, he was surrounded by water, right? But he couldn't drink that water, right? If you watch the movie, you know he made a little still to distill the water and get pure water or distilled water from the salt water, right? What happens if you're really thirsty and you drink salt water?
You become even more dehydrated.
You become even more dehydrated, right? The water goes through, so you know, if this is you, let's say, all right, you drink that salt water, and now you got this very concentrated solution inside your digestive tract, okay? You have that very concentrated solution. And what I say about concentrated solution, they are thirsty, right? They want water. So what's it gonna do? Instead of hydrating your cells, right? Your cells are gonna dehydrate. So here's one of your cells, and water's gonna move that way, right? So you're gonna get all this extra water in your intestine, and guess what that's going to lead to? Diarrhea, unfortunately, right? And so some laxatives work this way. Some laxatives are very, very concentrated salt solutions that you drink, and they draw in all this water, right? And they just make you poop like crazy, right? And so, and that's because I want you to think of this concentrated solution as being really, really thirsty. It's going to draw pure water to itself, right? So if you're ever stuck in a lifeboat with a Bengal tiger, right, don't drink the salt water. That'll only make it faster, right, for you to dehydrate. What you have to do is build a little still and eat the tiger, yeah. Build a little still and distill your water and drink that, okay? All right, so here's where I want you to think about it. Here's a concentrated solution. It's thirsty, right? It's going to draw pure water to itself, all right? And if you understand this idea, you'll be able to understand the colligative properties that we're going to discuss, okay? The first one we're going to discuss is vapor pressure lowering. So remember that a solution, remember that a pure substance like water has some vapor pressure, right? So if you have pure water, right, there's some water molecules above, right, which results in some vapor pressure. And remember, we learned about vapor pressure in the previous chapter, right? So vapor pressure is the pressure of the solvent gas above the solvent. The pressure of a substance. The vapor pressure is the pressure of the partial pressure of a substance above its liquid, right, in equilibrium, right? So when they're in equilibrium, that's the vapor pressure. And what do you remember about vapor pressure? As temperature increases, what happens to vapor pressure? Increases, right? Vapor pressure increases with increasing pressure. And remember, when the vapor pressure equals the external temperature, when the vapor pressure equals the external pressure, what happens? Boiling. Exactly right. Okay. Now, let's say I take a pure solvent. So let's just imagine this is pure water. And then I have a concentrated solution, right? If we follow the idea that the concentrated solution is thirsty, right? What's going to happen? It's going to want to take more and more of this pure solvent and get it mixed in here with itself, right? Just like the concentrated solution, when it passes through the intestine, draws in pure water. So this is going to draw in pure water, right? And here's what happens over time. It's really interesting. Over time, you're going to get the vapor pressure of the solutions up inside, and this level is going to go down, and this level is going to go up. Why? This concentrated solution is thirsty, and it's going to drink some of that water. And in fact, this will happen until this becomes completely empty, and all of that liquid will transfer from here to here. So that happens because at this vapor pressure, whatever the vapor pressure is of pure water at that temperature, is higher than this vapor pressure. This vapor pressure is lower. So at the pressure that this is releasing or vaporizing water, this is condensing water, right? And so this will just keep going. This will try to make it up to its vapor pressure, but since this vapor pressure is lower, this will condense, evaporate, condense, until eventually the whole thing comes over, okay? So this just is another view of that. The pure solvent establishes its equilibrium, okay, at some vapor pressure. The addition of a non-volatile solute reduces the rate of vaporization, decreasing the amount of vapor. And you're going to get equilibrium again, but only with a smaller number of vapor molecules. All right? So we can quantify that with an expression called Raoult's law. And Raoult's law says that the vapor pressure of a solution is equal to the mole fraction of the solvent. Now be very careful here. This is mole fraction of the solvent. In the examples we did before, we were always calculating the mole fraction of the solute, but you can also calculate the mole fraction of the solvent, right? That's just moles of solvent divided by total moles, okay? Mole fraction of the solvent times the vapor pressure of the pure solvent. So this is vapor pressure of solution. This is mole fraction solvent, right? And this is vapor pressure of pure solvent, all right? So suppose you had a solution that was 90% water and 10% some other solute, okay? So that the mole fraction of water in the solution is 0.90, okay? And you want to know, okay, what's the vapor pressure of that solution? Well, the vapor pressure of pure water, let's say at a given temp at 25 degrees Celsius, is equal to 23.8 torr. All right, so the vapor pressure of the solution, right, is just equal to what? 0.9 times 23.8 torr, right? And that's equal to 21.4 torr. So see what happened? We have a solution here that is 10% solute, 90% water. Yeah? What happened to the vapor pressure? It became 90% of the vapor pressure of the pure water, right? So if it was, 0.5% water, which means that, sorry, not 0.5%, but mole fraction of 0.5 water, then the vapor pressure would be half of the pure solvent and so on. Does that make sense? So in other words, the vapor pressure is lowered in direct proportion to the mole fraction of the solvent, right? The mole fraction of the solvent. All right, let's do an example. A solution, so we're given that a solution contains naphthalene, C10H8, dissolved in hexane, C6H14, at a concentration of 10.85% naphthalene by mass, right? And we want to find the vapor pressure, of the solvent. Okay, the solvent in this case is the hexane. Okay, we want to find the vapor pressure of hexane at 25 degrees above the solution. And then we're also given that the vapor pressure of pure hexane, so P0 hexane, is equal to 151 torr. Does that make sense so far? So of course, we're going to use this equation that we just talked about, Raoult's law, right? P solution is equal to chi solvent times the vapor pressure of the pure solvent. So so we're looking for the vapor pressure of the solution is equal to the mole fraction of what? Hexane or naphthalene?
Hexane.
Hexane, right? The solvent, always the solvent for this particular kind of problem, times the vapor pressure of pure hexane, which is also given, right? So we're trying to find this. We're given this, right? That's what goes there, right? So this boils down to finding the mole fraction of hexane. So let's remember, whenever you got to find any concentration, right? Write it out first as a ratio, right? So what is the mole fraction of hexane? It's moles of hexane divided by moles of hexane plus moles of naphthalene, right? This is the naphthalene. This is the hexane. Okay? So let's go find those things, right? Moles of hexane is going to be equal to 10.85 grams. Sorry, no, that's not right. 89.15 grams of hexane, right? And then the formula is C6H14, so we can get the molar mass from that. 1 mole times 1 mole over 86.17 grams. And our grams cancel, and I get 1.035 moles of hexane. Okay, moles of naphthalene. Let's see, I see a question. Alexander.
Yeah, wait, where are you getting the 89.15 grams from?
89.15 grams is coming from, okay, so if I have 10.85, good question, actually, I should have clarified that. If I have 10.85% C10H8 by mass, right? That means in a 100 gram sample, right, what do I have? 10.85 grams of methane and 89.15 grams of hexane, right? Because that's what that means. It means I have 10.85 grams of this divided by 100 grams total, right? So if I have 100 grams total, then I know that I must have 100 minus this of hexane, which is 89.15. Does that make sense? Good question. Thank you. All right. And then moles of naphthalene is equal to 10.85 grams times 1 mole over 128.16 grams. And that cancels and I get 0.0847 moles of naphthalene. All right, everybody with me? Is that making sense so far?
So the one that goes on the bottom of 1 mole, it is the molar weight.
Yes, this is the molar mass for those two things, right?
Do we
C10.
always assume it's to find the percentage of the other one? See how we only had the 10.85% and assume it's out of 100?
Yes, for this kind of thing where you have to convert, you basically have to convert from this unit, right, to this unit.
Okay.
So the way to always think about that is as ratios, right? What does 10.85 mean? It means 10.85 grams of naphthalene over 100 grams of solution, right? But what do you need for mole fraction? You need moles hexane plus moles naphthalene, right? So, okay, in this sample, let's just say I have 100 grams. In this sample, right, I have 10.85 grams of naphthalene. How many grams of hexane would I have? Well, it'd be 100 minus 10.85. Okay. Sorry, I didn't clarify that at the very beginning. Okay, so now I can figure out my mole fraction. Chi hexane, right, is going to be equal to what? Moles of hexane, 1.035, divided by what? 1.035 plus 0.0847, right? Because it's moles of hexane divided by moles of hexane plus moles of naphthalene. Okay, and that comes out to be equal to 0.9244, right? No units. Okay, so now I'm ready to go. P solution, right, is equal to what? 0.9244 times the vapor pressure of the pure solution. Where'd I write that down? You see that right here, 151 torr. Sorry, the vapor pressure of the pure solvent. Vapor pressure of the pure solvent, right? 151 torr. So that's times 151 torr, right? So in other words, again, because the mole fraction of the solvent is 92% of the total solution, the vapor pressure is going to be 92% of the vapor pressure of the pure solvent, right? But of course, when you do percentages, you change it to fraction. So this turns out to be 140 torr. Does that make sense?
So one question, when you were on the two glosses that had different, like a pure solution and a non-pure solution.
Yeah.
So the vapor pressure of the pure solution is lower than the vapor pressure of the mixed solution?
The other way around. So first of all, this is the pure solvent, and this is the solution. And the vapor pressure of the solution is lower than the vapor pressure of the pure solvent, right? So how do we think about that? If you just think about a pure solvent, right? It has some vapor pressure. Now, if you think of a solution, the solution is thirsty. What's it thirsty for? More of the solvent. So what's it going to do to the vapor pressure? Lower it. Does that make sense?
I don't know why I'm not figuring out why it would lower it.
Well, I haven't given you the fundamental reason because the fundamental reason is due to entropy. And it's basically because nature doesn't like pure stuff. It likes everything mixed up, right? So if it can mix it up, it'll mix it up. And so what it does is, even in this case, it'll take this and mix it up with that. That's the fundamental reason that it happens. Taylor.
Is the speed of that dependent on temperature?
Yeah.
Like if you heat that up, will it
Correct.
go
Absolutely.
faster?
Go faster.
Okay.
Yep. Absolutely.
Okay.
Yep. Let's see, other questions? Okay, I want to ask you a couple of conceptual questions. I want you to think about these carefully. So let me launch a poll here. And these are just conceptual questions. I'm not going to have you do a calculation, but I just want you to think about this. So you have two solutions. One has 10 grams of glucose in 1 liter of water, and the other one has 10 grams of sucrose in 1 liter of water. So you have two different solutions. They're not going to have the same concentration. Why? At least they're not going to have the same mole fraction in terms of concentration. Why? Because the glucose has a lower molar mass than the sucrose, right? So 10 grams of glucose is fewer moles of solute than 10 grams of sucrose. Other way around. Sorry, I just totally confused you. 10 grams of glucose is more moles than 10 grams of sucrose. Okay, so that's what you got to think about. Which one has them? And then you should be able to answer this question. Which solution has the higher vapor pressure of water? You don't have to do any calculations. Just think about it. Remember that the vapor pressure of water is equal to the mole fraction of water times the vapor pressure, the vapor pressure of the solution is equal to the mole fraction of water times the vapor pressure of pure water. So this question boils down to figuring out, okay, which of these two solutions has the higher vapor pressure, the higher mole fraction of water? This one or that one? Okay. A lot of you are answering that. Let me give you another hint here. So the solution that has the highest vapor pressure, right, will be the one for which this number is biggest. Correct? Again, the solution with the highest vapor pressure will be the one that has the highest mole fraction of water. Here's the formula for the mole fraction of water, right? It's moles water over moles water plus moles of solute. Which of the two solutions is going to have the highest Chi H2O? The one that has the smallest number of moles of solute, right? Which one has the smallest number of moles of solute?
Because vapor pressure decreases when you have more stuff dissolved in it, right?
Correct.
Okay.
Right. Exactly right. Yep. So I'm going to end the poll here. A A lot of you got it, but some of you didn't, right? So some of you put glucose, but the right answer is actually B, okay? The right answer is sucrose. And again, why is that? Because 10 grams of sucrose is fewer moles than 10 grams of glucose, right? Why? Because look at sucrose, C12H22O11, it has a higher molar mass, right? And since it has a higher molar mass, if I have 10 grams of both of them, right, this is less moles. So 10 grams sucrose is less moles than 10 grams of glucose, right? So for sucrose, this number is going to be smaller, which means this number is going to be bigger, which means the vapor pressure is going to be bigger. Does that make sense?
So
Kind of hard to think
sucrose
about. Go ahead, Gabby.
So because sucrose has more moles than glucose, it has less, more molar mass than.
Yes, correct.
Correct, it has less moles.
Correct.
Okay. Yeah.
Correct. Yep. So that solution is going to be less concentrated, right? So it'll have a higher vapor pressure. Abe.
Wait, why is it that we can like ignore the pressure of, I guess, water in this case?
We're not ignoring the vapor pressure of water. That's what we're trying to calculate.
Oh, wait, are we saying that the pressure is the same? Like the pressure of the solution is the same?
As what?
So basically what I'm trying to think of is like, let's say we're comparing like, I guess the solution that the glucose and water will make and the solution that the sucrose and water will make.
Correct.
Are we saying that the pressures of each solution is going to be the same and we're just comparing them based off the mole fraction? That makes sense.
So the vapor pressure of the pure water is the same because that's just the vapor pressure of pure water, which is a constant, right? At a given temperature, the vapor pressure of pure water is 23.8. Let's say at room temperature, it's 23.8. So this number is 23.8 for both of these, right? Because that's just the vapor pressure of pure water. So the vapor pressure of the solution will depend only on the mole fraction then, right? Whichever one has the highest mole fraction of water will be the one that has the highest vapor pressure. Now, the reason this is a little bit confusing is because you're thinking of the mole fraction of the solvent, right? So the highest mole fraction solvent is the lowest mole fraction solute. Correct? Okay. So the lowest mole fraction solute is a sucrose solution because you have fewer moles of sucrose than glucose.
Yep. Got it. Thank you.
Okay, good. All right, so that's that question. Let me ask you one more question. And this relates to what we talked about at the very beginning. And so what I want you to think about here is now you have two solutions. Your glucose solution from before, which is 1 mole of glucose in 1 liter of water. All right, but now I'm talking about moles instead of grams. And then this one is 1 mole of potassium bromide in 1 liter of water. But now you got to remember, glucose is molecular, right? So when 1 mole of glucose dissolves in water, how many moles of dissolved particles do I have?
One mole.
1 mole, okay? But potassium bromide is an ionic substance, right? So when 1 mole of potassium bromide dissolves in water, how many moles of particles do I have?
2.
2. All right. So based on that, which one has the higher vapor pressure? Don't answer on the poll. Okay, just another 10 seconds or so, put in an answer. And I'm going to end it right here. All right, good. The majority of you got the right answer. The right answer is A, right? What happens here is that 1 mole of glucose in 1 liter of water, right? Compared to 1 mole of potassium, which is 2 moles of particles, right? So which solution is more concentrated in terms of particles? The more concentrated solution is the potassium bromide solution, right? So the more concentrated the solution, the lower the vapor pressure. The less concentrated in particles, the higher the vapor pressure. So therefore the glucose, which has the fewest number of dissolved particles, is going to have the higher vapor pressure. Okay. All right. Very good. Very good. So the answer is A. And then let's see, we're almost out of time. We still have a few more colligative properties to look at. But remember, these properties are properties of solutions that depend on the number of dissolved particles. Okay. And so we'll continue with that idea next time. We're going to look at freezing point depression, boiling point elevation, and osmotic pressure. Those are 3 more colligative properties that we'll look at next time. Okay. Thank you all so much for your attention. Let's see, higher concentrated solution equal lower vapor pressure. Correct. The higher the concentration of the solution, the lower the vapor pressure. The weird thing is that this is always the mole fraction of the solvent, right? So the more concentrated the solution, the lower the mole fraction of the solvent. So therefore, the lower the vapor pressure. Again, it all comes back to thirsty solutions, right? The more concentrated the solution, the thirstier it is, and the lower the vapor pressure is going to be, right? Why is it thirsty? It's going to drink up its own solvent, right? If it drinks up its own solvent, that's going to lower the amount of particles that are above the solution, so it's going to lower the vapor pressure. All right, very, very good. Our time is up, so I am going to officially end class. Of course, I will stick around for as long as you need me for any questions. Remember, you can always contact me if you want to have additional help. I'm available, especially Tuesdays and Thursdays from 2 to 4. And so you can contact me and we can set up a Zoom call and you can ask more questions. After class, I always stick around for as long as it takes to answer everybody's questions. So after class, you're always free to stick around and ask any kinds of questions you would like. Okay. Thank you all very much. Have a great afternoon, and I'll see you all again on Wednesday. Bye.
Thanks, Professor.